Okay, I
All
think we're
right.
good to get started.
Yeah, I think we're good to get started. You can go ahead.
Cool. All right. So I see some new faces, at least on my end. So for anyone who I haven't met yet, my name is Brittany Hernandez. I am many years into the Research Methods Measurement and Evaluation program. And so just a little bit about like what brought me here to this specific workshop today was Kylie and I were working on a project where we're trying to prompt llama models. So llama is kind of like the chat GPT equivalent of that Meta has created. They're slightly smaller, well, not slightly, they're smaller models. But one of the nice things is that instead of using like an API or like GPT's resources where we send our inputs to their server system and then get outputs back. Instead, we can actually download llama models like on our computer. Say that in quotes for now because it's kind of why we ended up in HPC land. So we can download them locally and then actually run the models in kind of like a contained ecosystem where we actually are the only ones that like have access to that like input output stream. And so kind of what's ended up happening is that Llama has multiple models, the most recent of which is 3.3. It's a 70 billion parameter model. For reference, I on my computer can run about a 1 billion or a 3 billion parameter model. So this model is chunky and does not work on my computer, which is how we ended up in HPC space, which is why I've kind of spent a lot of time really through lots and lots of errors and struggle trying to figure out how HPC works and how to make job requests and, kind of started dabbling in a very, very, very shallow understanding of like hardware. But so my hope with this workshop was just to kind of give that information that I've learned thus far in this experience for anyone else who might be using HPC and maybe containers, which is one of the ways that we install software on HPC. So before I go forward, I'm going to pause to see if there's any questions or thoughts or comments thus far.
Okay, one thought and comment, which is that thank you to Brittany. And I just wanted to say that all that you figured out this semester is really, I don't know, some relentless problem solving. So really impressive work and makes me think you can be dropped into any scenario and you'll figure out your solution.
Thank you. I appreciate it. I appreciate your faith in my problem solving, even though sometimes I don't always believe in my own problem solving. So, I do really rely on that. Okay, so I'm gonna share my screen and hopefully you see a little slideshow. Can I get just a thumbs up from someone?
It's there.
Yeah. Okay, cool. Okay, so a little bit. So this is kind of like still the slideshow is finished up. The GitHub repository is still in very much just like written text form. So as we kind of talk through this workshop, my thought is I'm going to incorporate, so the presentation is really just all pictures for me to kind of support talking through this. And then the GitHub repository is like all text. So eventually those two will merge. So eventually all the images we see on this presentation are going to go in the GitHub. And yeah, it's still in a little bit of working form. So just a little forewarning, but you have kind of, I think, I tried to be a little more comprehensive in the documentation that I've provided on the repository. So I don't necessarily expect y'all to follow along that text as I go, but just know that you have it there as a reference. So intro to UConn Storrs HPC, and then we'll kind of end on how we install software on it. Okay, so as I kind of mentioned, HPC is going, like, we're leveraging it to do things that like our personal or our work computers are doing. So I think I saw in the survey, like one person wants to run Monte Carlo simulations on it. We're particularly using it in order to like host containers with llama models on it, and then actually communicate with those models within the HPC environment. And so HPC is like kind of built up of this cluster of different partitions. And these partitions are actually like linked to physical resources. So they have cores and RAM. And so they're every single node that we see in each of these partitions, and sorry, I kind of skipped over. So the partitions are characterized by certain features. So like the general partitions are going to be kind of multi-use, multi-purpose partitions. So all the nodes, if you see in the little like bottom portion of the graphic, there's tinier squares that tell you how many nodes are in each partition. I've also kind of color coded it because they have certain certain like features that they're associated with. It doesn't matter too much right now, but as you're navigating, like if you're navigating the UConn Storrs Getting Started guide, you'll kind of see there's like other features that might be important as you're working within like different types of tasks that you want to do. So for example, the like GPU, if you're doing something with graphics, I don't expect we're necessarily using graphics, but like a GPU would be kind of optimized for something where you're using a lot of graphics and you need a more powerful and more specialized processor. And so each of those nodes listed are affiliated with like physical resources. So we can think of like on the left is our processing unit. So the processor, I like to think of as sort of the brain of our computer. It is the thing that is executing tasks. When we go to like open an Excel file, it's the thing that says to like open Excel, open the file itself. Now, the file itself is saved on like the hard drive, so some sort of like hard storage. But when we want to queue up that information to actually be used in an application like Excel, anything saved on like our hard drive gets actually moved to RAM, which is random access memory. And so the way I like to think of RAM is it's sort of like borrowed storage space for the processor to use, and it's more readily available and it's faster. So while it would take a lot of time for your CPU to go fetch information from your hard drive, it's actually faster for it to access it in RAM. So anytime your computer is doing something, it's actually moving that information that's stored in like long-term storage to a more short-term, more accessible space. And so I'm not just brain dumping this on you for funsies, because it does end up becoming important when we request jobs, which is kind of the next section that we'll talk about. So there's kind of two ways to make job requests in HPC. So there's an S run, which I have this little cat on a parachute because I like to think of it as like a drop-in. You don't have to schedule this time. You can, we all could right now go to HPC, request an S run job and drop in. And the other like notable feature is not only that it's a drop-in format, but also you can interact in real time, like send outputs and receive, or send inputs and receive outputs from HPC in real time. That does not work in SBatch. SBatch, you actually schedule time and resources. So you might say, I want a certain number of cores and RAM, And whenever those resources become available, here is the thing that I want you to do. And so you give that, maybe it's a script, maybe it's multiple lines of code telling it to like install requirements and execute a script. You would send that with an SBatch, and that job would run whenever those resources become available. But you actually have to schedule it, and if it fails, you won't be able to do anything about it in real time. You'll have to wait to, you'll get an email from HPC that says your job failed, and then you have to go fix it on your own and reschedule a new job. So my workflow, and what I'll talk about a little more in depth today, is actually using SRun for the most part. And so when I say like that we're scheduled, like when resources become available, behind the scenes at HPC, there's this application called Slurm, S-L-U-R-M, that actually determines how to allocate resources, because UConn HPC is a shared resource amongst all faculty and students. There's going to be overlap in like maybe needs, especially on the general partition. And so when you go and make a job request, behind the scenes is this little application that takes into consideration how many job requests you've made, how big your job is, how many resources you're actually requesting, and determines whether or not to actually like approve that request or not. And then also one thing just to note is, in my experience when using SRun, there are chances that you get kicked off if for someone else that's higher priority. And so it's only happened to me a couple of times, but there are occasions where running SRun, you might get kicked out in the middle of trying to work through something, while as SBatch you don't have that same problem. So just a couple trade-offs, but again, my workflow tends to be SRun. Okay, so basically what we'll be doing is we'll be sitting on our computers, and then we're going to use Terminal in order to actually access HPC. And when we do that, we're going to be assigned a node that's just for logging in. And once we log in, we're going to then create that job task. And so that job task is this line that's here that says SRun. So this matches the SRun that's here in the little parachute cat. So the first command is SRun. You can set a time limit. Also just note, these are not the only pieces of information you can add into the request. There's a larger Slurm guide that's linked in the GitHub repository, but here's just this is just a little example. So you can specify a time limit, which is something I like to do in case I forget to exit out of a job. It won't just stay forever until I get kicked out. I try to be mindful of the fact that these are shared resources, and so trying to be like very intentional with how I request those resources and how I request time. You can specify the number of nodes you want to be on and how many cores you want. If you specify cores, you're going to want to specify that whether or not they're all coming from the same node. And then you specify how much memory. So you might request, you probably wouldn't be just requesting 8 gigs, but you might request 64. And that would increase the speed with which any tasks you're trying to execute would run. And then this last line here is telling it what language to communicate in, which is Bash script. Okay. This next section, I think, is to me, the hardest concept to kind of get my mind around. So, I mean, one, please ask questions if you have them as of now, but especially in this section, ask questions if things aren't making sense. So there are different ways we can access software within HPC. So there are modules, system packages, and then external software, which I'm going to leave as like kind of we'll talk more about that later. So system packages are going to be one version is available of an application for the entire like global environment of HPC. So everyone has access to that singular version of the application. Modules are going to be for something maybe like Python or R are installed as modules. You might want different versions of R or Python depending on what you're actually trying to do. And maybe you're trying to mirror something on your computer, so you might want like a specific version of Python. So the modules are actually going to have multiple versions of different software available, but they're preloaded by HPC. So you don't have to do anything except for like load them in the same way that you would load a package into R or Python. Now, external software, so anything that isn't available as a system package or a module gets kind of classified as external software. And there's a few different ways to install software, one of which is using a container, which is what we'll talk about. And so the way I like to think about containers, so we're going to ignore the images part for right now, but the container I actually like to think of as its own mini computer specifically meant to run a singular application. So it would be as if you like on your computer deleted every single application you had and only put R on it and anything that R needed to run, or Excel or Python. So I like to think of the containers in that way. They're really just meant to run one application, and they do it really well. And they also standardize the environment. If I make a container on my computer, it's going to have the same features as when Kylie or Betsy makes the container, as long as we're making it from the same image. And so the image is going to be sort of the instructional manual. The image is the thing that tells it what R needs in order to run. It's beyond my scope of knowledge. I have tried to build an image from scratch, and it's a nightmare. So the nice thing is that a lot of these software applications are readily available on Docker. So there is a Docker Hub library of applications or that are available, like have images already pre-built. So they're kind of like templates. Like I'd like to think of images as instructional manuals, templates, the thing that tell it what features the computer to serve maybe like R or Python are. And in this case, we don't need a container for R or Python because HPC has it as a module. But what happened with the project Kylie and I are working on is we want to use an application called Ollama. Ollama helps us run llama models really efficiently. But the problem is it's not available as a system package or a module. Now, we have the image, like there is an Ollama image that's already created on Docker. Now, there's two ways that we'll talk about right now to actually build that container from that image in the Docker library. One of them is we can actually build a container locally. So I can go onto my computer, I can go to terminal, I can run a couple lines of code through terminal, and I can have a container up and running that specifically is used for running Ollama. And that just sits on my computer. It's kind of the equivalent of like installing an application. Now I have access to it, I can run it on my computer. When we move to HPC, we can't use Docker to actually build the containers. they have a system, now it's a system package called Apptainer, which is used, it's an equivalent of Docker, but it's used specifically for HPC environments to build containers. So when we actually do the build for the container, we're going to use Apptainer to do that, but we're still going to be able to go and reference that original Docker image. So whether we're using Docker or Apptainer to build the image, we're going to still be only ever using that Docker image. So the computer build might be built by a different application, but it's going to have the same features because at their origin, they all point to that same image. And then what we'll be able to do is actually similar to how we like go and shell into HPC. So we'll like kind of create an access point to go into HPC. We can then shell into the container, create an access point to it. And now we go in and we can like open Olama and we can download a model to it. So different applications will have different things. If you go into the container, you can run things in it. Okay, so we're about halfway through, which is what I was hoping for. We have some time for a little demo to play around in HPC space. We also have time, you know, like if people have specific things they want to do with HPC that they want to kind of conceptually talk through, we can do that. I left this space to be flexible to what people need. So I'm going to stop talking now.
Does anybody have any questions for Brittany?
I just have a quick question. For the most part, are these processes similar whether you're using Mac or Windows?
Kind of. So you can get to that place. There are slightly different applications that you're going to need to have installed depending on if you have a Mac, Linux, or Windows computer. Mac and Linux end up being quite similar. So for example, let me actually share screen and I'll take us to the oops. Me and the UConn HPC site have gotten well acquainted of late. So in this getting started guide, so this is on the UConn knowledge base, they have this getting started guide, which actually makes it really nice for actually setting, I found it very nice for setting up the software. Something that I found difficult actually when navigating it is I wanted like a step-by-step for like, what exactly do I need to install? So that's where I've kind of like created this GitHub repo. So these are all the context and prerequisites. I list my OS just to kind of make note of exactly what you were talking about, that it will be slightly different. But for the most part, I think the only place it really comes in is related to this X quartz system. So for Mac and Linux users, you use this it's called a secure shell client and X11 Windows system. What it is it's basically how it's how HPC sends graphic outputs to your computer. So that's what's needed. So that ends up being the point with which they differ, but a lot of these are the same. The Docker count, FileZilla is going to be the way that you actually like upload files to HPC. That's going to be the same whether Mac or Windows. And we've found workarounds a little bit for it. So like we've been working, so I work on a Mac, Kylie works on a Mac, Claudia, who's also on this project, works on a Windows computer. The way that we've kind of found to simulate all of our workflows into like one template is actually working through the command through terminal in Visual Studio Code. So we actually run all our lines through terminal. And so if you go back to this getting started guide, when they say,
Brittany, you're not sharing the getting started guide. Is that what you wanted to share?
Yeah,
oh
I
my
was about to say
gosh,
that.
yes, thank you. Thank you. This is what happens when I have two screens. Don't know which one's which. Okay. Okay, here. So this is where you would download and install on a Mac, and then instead of this Xquartz, it would be MOBA Xterm, which is what you would use in order to kind of connect to like shell into HPC.
Thank you. Yeah.
Okay, I think if we don't have any questions, I'm just gonna take us through requesting a job and maybe like looking around HPC. That's what I found super helpful when I was initially going through. Just a note as I do this, I have followed the getting started guide and I have all the software that are listed in that like context and prerequisites section. And that was done with the getting started guide. Okay, let me, okay, I'm gonna share the correct screen. Okay, we will go to, yeah, this is the FileZilla, and then we're gonna go to, let's go secure client. So this is, just so we kind of start fresh, this is how we actually, so in order to shell in, we need to be connected to UConn Storrs Wi-Fi. So the first step is actually connecting to a VPN if you're off campus. So I connect to the VPN, it prompts me for a username and password, which is also going to be something that you need a lot. So I found it very nice to have a password manager because the password comes up so often. Okay, and then we're gonna go to terminal. And I'm pull up the GitHub so that we can kind of see where these are. So I've set it up so that in resources, there, one moment, please. Demo steps. Now there's going to be demo steps. So there's these steps. So I have a copy of these steps that is saved on my like local computer where I've like input my net ID, and these take us through kind of one by one what you need to do in order to run the demo that is, it lives on this HPC workshop. There's this artist ID. So I've used here Olama. I've put in it just like kind of a data set, a data set of 3 songs, and in it are the lyrics of 3 songs that I like, and then the artist and what I do is I ask the llama model to then try to predict and tell me who the artist is based on the lyrics. This was just a little small thing to play with. And so this is the code that does that. So it asks the model, I'm going to provide you lyrics, tell me who the singer or band is, and then it loops through and does that. Okay, so that's what we'll end up doing conceptually. But so first we connect to UConn Secure Wi-Fi. Next, we're going to log into HPC. Reference my copy of this. And so we'll shell in. Again, give password. And then, so the way that you know that you are in HPC, other than this like giant welcome text, is that you've been assigned a login node. And so this like initial prompt for an input has my net ID at the login node that I'm in. And we can also check what the login node, sometimes it'll say like bash for the script. So like it won't always in this little initial prompt say that, but one way that we can check what node we are on is by running hostname. And that'll tell us that we're at the Storrs HPC address and we're on login node 5. And so on this, I can list any files that exist in my HPC account. So the command ls tells me list, I believe. So there's some in the resources folder. Some of these that I'm pulling up are in this HPC. So this says like how to navigate around, just random commands that I've found very helpful. So I've done lists. This tells me what folders are available. So these are all folders. I've cloned this repository here, which is this folder. And then what I can do is actually like change the directory. I can go into that HPC workshop folder. HPC workshop. And now I'm in it and I can list the files here. So this will mirror what is available here. So we see data, we see data, we see requirements. And then something I like doing is actually changing the directory. So what helped me get a little bit of an orientation to like where I live in the larger space of HPC is actually like going through some of the parent directories. So if we do cd ... we can keep going up. And then let's just do ls. So this is kind of like where we end up. So these are all the files that exist in HB. There's this scratch folder, which is where short-term data gets stored. So if you're running things that need a really quick place to store data or store information, it can go, or not data, but like output, it can go to the scratch folder. And then we can go to the anything in Scratch gets deleted after 90 days. And so you move it to shared. So these are like the locations. So what I've done is I've used some of these like understanding of the parent directories and like navigating on HPC in order to try to orient myself to where I might find certain folders and where like my account lives. So we can backtrack to we can go to CD BH 17005. Let's see, I think it is in User. PD. PD. H1705. Okay, so now I'm back to my little login node. And so now we can actually do a job request. This is where we create jobs. So I'm going to do an interactive job. And so this we're requesting just a 30-minute job. We could bump that down to 20 minutes because we only have 20 minutes left in this little workshop. And then we're asking for 32 gigs of memory. So now it said, so it happened quite quickly that we got resources, but it told us that it's waiting for resources. So that is that like behind the scenes, that's Slurm determining like what resources are available. And then we've been allocated the resources. Now, this has been resolved recently, but there was an error message that was saying something like failed, and it was making it seem like the job didn't get allocated, even though people were assigned a node. So if that happens, I like to just check what node I'm on after I request resources by doing host name again. And this is the node that we've been assigned. So the node name is called CN627. And what we can do now is we can take a look at the different modules that we have. So if we go back to resources and go to HPC, you see here there's some information about modules. So we can do module avail, which kind of gives us a massive list of all the modules that are preloaded. You'll see a version number off of these like duplicates. And then we can take a look at module. Not sure why it's not letting me type. All right, one moment. This is not. Letting me type. I think my computer bugged out a little bit. Okay, we're gonna terminate this real quick and just kind of quickly start fresh.
That happened to me, Brittany, when you go to module list. Somehow, I don't know, I think it doesn't work. I did it twice already, and I just need to close everything down.
Oh,
I thought maybe it was going to
interesting.
work for you, but for some reason, module list does that, just to let you know.
Which is so weird. Yeah, I think because that's a new little bug. But that's good. Does it do it when you're just looking at like a specific program? Like if I go to do module list Python, will it do that?
Oh, I didn't try that. I just tried
Okay.
module list and tried to exit from that specific part, but yeah, it didn't work out. I need to close everything down when I go there.
Let's see. And I think I have a running job. So let's see if I can grab that node. Okay, that exited when we closed out. So that S jobs kind of asks what jobs that I have running that I've requested. And so I kind of use that in order to see, since this bugged out and I wasn't actually able to exit out of the job that I was running, I've like made sure that that job kind of closed out and those resources aren't just like idling for 20 minutes. Because if that job was still running, we could actually just shell directly into it, which I will show in a second once we figure out the module list. Okay, so we're gonna ask for the same amount of resources again, do srun, and now let's try module avail Python. And so I think there's a couple different versions. There's this 3.12.5 version. And something I found is like not always, the packages can sometimes be incompatible. So like for example, for the demo, we're gonna actually go through unloading a couple modules and loading a couple modules because there are dependencies within them that actually have like conflicts. And so what you can do is either is like unload each individual module, or you can then go and do something called module purge, which is here, which removes all modules that you have downloaded, that are like downloaded. Okay. And now we will, is there anything people want to see? I'm kind of just bopping around. So if anyone wants to see anything, otherwise I'm just going to go through and finish the demo. Okay, so then we go to module build. So in this last command, when we've like loaded these modules, we downloaded Apptainer, which is the service that we're using to build containers. We also downloaded Python, which is going to be the service that we're using in order to run that script. And then there's a module called GCC, which is a dependency of both Apptainer and Python that needs to be compatible to both Apptainer and Python. And so now what we're going to do, we have Apptainer available now. And so we're going to actually build a container. And we can enter through. So I have a Docker account. For people who don't have a Docker account, you don't have to connect the container build to your Docker account. So if you don't want to, you can just press enter through these, and it's going to start building a container from the image. And the image lives on dockerhub.com. So if we go to Docker Hub, we see this path here, Olama is the same path that we specified in this run that said Docker // Olama. The only thing additional we have is that we have this latest, which just tells it to grab the latest version of that image template that we're using. And so now when I build this Docker image or Docker container, when Claudia builds this Docker container, they're exactly the same because they've been built from the exact same image. So when something runs in it, we know it should be running exactly the same for me and for anyone else who has built the container that same way. And so this will take a minute. It will take a second to build. I believe we're close to being done. And just a prelude, so once this finishes running, let's take a look at the code quickly. So we've done Docker build or Apptainer build. Apptainer build is essentially saying, like, you know, if we're thinking of containers as little computers, it's saying build this little computer, and do it based on the instructions at Olama in the Docker Hub. Now, the next thing we're going to do once this finishes downloading is we're going to run Apptainer instance start. And what Apptainer instance start does is it's kind of the equivalent, if we're using the analogy of a container being a computer, it's analogous to starting up your computer. So you're essentially like starting up the container. You're telling it. So what we've done is we've created the Docker container in a folder called Olama. And so when we list out the things that exist in my HPC account, we're going to see a folder called Olama, and that's actually the container that we've built. Now we're going to start the computer, the container, and we're taking it from this folder, from this Olama folder, and we're giving it a name. The name can be anything. In my case, I'm very on the nose and I call it Olama instance. And now we get a note that it's been started correctly. And now we're actually going to go into the container. So this would be like, you know, we've opened up, we've built the computer, we've started it, and now we're like actually going into it to start using it. And so now we see instead of bash 4.4, it says Apptainer. That tells us that we're in the container. And so we can do Olama help, so because this container specifically is built exclusively to run the Olama application. And so now when I do Olama help, I can see the different commands that I can do within this container. I can start Olama, which is starting, like opening and starting the application. I can create a model. I can start and stop models. I can run them. And so what we'll do is we'll actually just start Olama. And so what happens is when we start Olama, it actually takes up our entire terminal. This is what is supposed to happen. And we actually need to do the rest of the demo on a secondary window. So what we do is we grab, so we're going to want to do the rest of the demo on the secondary window, but on the same node that we were originally assigned. And so we're going to grab, we did host name somewhere. It's been allocated resources. Oh, we maybe didn't do it this time. Okay, let me Control C. We'll exit out of. So now Olama isn't started, and we're going to do host name. And we're on CN614. So now I'm going to show us just how to shell in directly to this node, and then I think we can end for today. Okay, so then we will shell in. We do the same thing that we did before, which is enter our like net ID and password. We go to the login node. And so now we've been assigned a login node, and we actually can just do SSH, which is the same way we got to Apptainer. And then we can take the name of the node we were on. And now we get this prompt to add it to our fingerprint. And now we are on that same node in two terminal windows where Olama is, well, now it's not open and running, but if I hadn't canceled it, it would be the same location where that application was open and running. And now I can go and do things like pull a model and actually like run commands against it. So that's how you'd finish up the demo. And I'm going to stop here because we're 5 minutes to, and just give time for last minute questions. I know it's a lot of information and a lot of dense information.
That's why we're glad we recorded it.
Yes. Okay.
So Brittany, since I think a lot of people want to be using want to conduct simulations, right? That's why they want to use the
Yes.
HPC. Can you note, I don't know, tell us a little bit about what that might look like. It sounds like it's easier because R is already
Installed.
mhm. But
Yeah.
data is maybe an issue or no? Like do they need to sign up for the data storing, essentially, is what I'm asking?
They might. So there's a limited amount of storage that you get just on your drive. So if things like are large, then that's where you would use, Scratch and shared. And yes, Scratch. So the thing is, both Scratch and shared, you need like approval for. So conceptually, it would be easier to log in. You would have your simulations in R. And then your output files or like your output paths would be slightly different, and they would take you not to that like kind of workspace we were originally in, but they would actually take you up to that Scratch and shared space. And then there are additional tools. There's an application that called Globus. So the place that you actually like save things to is the Scratch. It's always going to be Scratch. And then once it's in Scratch, you have 90 days to transfer it over to shared before it gets permanently deleted. So that would be the extra step that, especially on the like output side, I think with a simulation that we would be thinking about.
Can you also provide some guidance on what you've learned so far about like recommended cores and or number of nodes?
Yeah, so I've actually still been kind of feeling a little off on this because some days things run with like I can run a 3.2 model, which is 3 billion parameters on my computer in 3 minutes. Some days I can run it in like 20 minutes on HPC. And other days it like for Claudia, it's not running at all in like a 2-hour window. So I haven't 100%. So some of what I've seen online in just like discussion forums are that like sometimes the Slurm application on the back end can be a little buggy and actually like kind of allocate too many resources out that it can't support. And so there might be too many people on that node at the same time that are trying to do things. I don't know 100%. But what I found is often, so for what I'm doing, it tends to be fun to have one node. The other thing to like kind of plant as an idea is you can actually parallelize processes to make them go faster. So as opposed to, for example, the script that I have right now actually runs one. So there's 3 cases. So 3 songs that it asks the model to identify the artist for. What it does is the way that I've built out the loop in the script says start at 0, go to 1, wait for 1 to be done, go to 2, wait for 2 to be done, go to 3. What you can do is you can actually parallelize those processes, and those can sit on different cores. So you have one core doing the work of, number 0, you have one core doing the work of 1. And obviously you're not doing it at this scale, but in concept, you would have a core to run each kind of command. And so that would be another way that as we're thinking about running simulations, you might be parallelizing. And like another thing that I've been trying to do is, because I don't feel like I have a full grasp on how to manipulate the speed with which my tasks are running. I've been trying to add to my scripts checkpoints and track the RAM and CPU usage in order to try and get an estimate of on my computer. So while I don't have a concrete answer for what why certain things work well sometimes and not, and what I don't necessarily think I have recommendations on what to request, and but I can try to guide that problem solving. And if anyone knows more, please let me know. Okay.
I have a question.
Yeah.
Yeah, so kind of building on Carly's, is there like an IT service for HPC, or do you just have to figure it out on your own?
Yes. So there is HPC has admin who like kind of support questions. The one thing that they say is that like the admin don't know the task that you're trying to do or the software that you're trying to load, especially if you're loading external software. So there's kind of a limitation in what support they can actually provide because there's so many things that are being done with those resources. You know, one thing I found to be really successful as I'm working with admin on problem solving certain things is really, really meticulously documenting what I'm trying to do with lots of screenshots. I save my terminal output every time I run into a problem, and that way I can send it to the admin when I open a support ticket. And kind of say, so like I found them really helpful for like bugs. So when I get an error message that says I have an incompatible package, or when I see an error message that I don't think should be there, I find it really helpful. I think where it can be hard and where they don't always have tangible fixes is, for example, I was running into that piece where Olama, I have to like start the application in one terminal window and then actually download the models in a secondary window after it's been started. Like I ran into that, and it took us a while to actually, like, me and admin going back and forth trying to figure out what's going on, just because I kind of had to spend a bit of time onboarding them onto what I was trying to do because they're not experts in that. So they're great and super helpful, super willing to help. Also, just know it can be a little bit of work just to try, because they're supporting a lot of people doing a lot of different things.
Great, thank you.
Yeah, you're welcome. Yay. Well, as people learn more about HPC, and hopefully more than me, you know, that GitHub repository is also a space where, you know, I've added comments. You can, you know, update code directly in there. Like I really am thinking of that as like a working space for not just me, but anyone else who's working in HPC. So, you know, if you see things that you found a more efficient way to do, or you know, things come up as you're maybe using HPC, like please drop it in comments, add scripts to that GitHub repo. Like that's what it's there for, and I want it to be used. So thank you all for joining me.
Thanks so much. I'm gonna stop recording.